When an operation relies on reactive maintenance, the team spends its days running from one unexpected breakdown to another. The machine grinds to a halt, the alarm sounds, and the maintenance crew acts as an emergency firefighting unit. To build a mature, risk-based maintenance program, we have to stop reacting to the loudest alarm. Instead of simply doing more work, the goal is to execute the right work at the exact right time, based on evidence. Before building that strategy, you need 3 prerequisites. Step 1. A complete and verified asset register. Step 2. Historical data on how your equipment actually fails. And Step 3. Access to your CMMS or ERP system to execute the plan. With those 3 pieces secured, you can stop relying on organizational habit and start documenting a sustainable, highly reliable maintenance strategy. No facility has unlimited time or budget, so we first have to filter the workload. We do this using an objective scoring system called asset criticality, which dictates exactly where we should invest our maintenance resources. This chart is the risk matrix. On the y-axis, we plot the business consequence of an asset failing, factoring in safety, production loss, and repair cost. On the x-axis, we plot the historical likelihood of that failure actually occurring. Assets that land in the high-risk zone automatically trigger a rigorous reliability-centered maintenance analysis. Conversely, assets with low risk scores bypass this heavy analysis and receive standard routine servicing. For those high-risk assets, we have to isolate exactly what goes wrong. We cannot use vague terms like pump failure. We need highly specific descriptions of how the component fails its intended function. This table is a FEMECA worksheet. First, we list the function. Next, we map the precise physical failure mode. For example, bearing failure due to contaminated lubricant. Finally, we record the visible effect that occurs when that failure happens. Pinning down that specific physical root cause is the mandatory first step. You can only assign an effective, proactive maintenance tactic once you know exactly what mechanism you are trying to prevent. Now we match each mapped failure mode to one of the 6 core maintenance tactics, aiming for a proactive approach wherever possible. Our first tactic option is time-based maintenance. We apply this tactic only when a component demonstrates a predictable, age-related wear-out pattern, allowing us to schedule a replacement at a fixed interval. This graph is the PF curve. It tracks an asset's condition as it slopes downward over time. When we can measure that degradation through vibration or oil analysis, we use condition-based maintenance to order a replacement just in time. Look at the specific window between P, the first detectable sign of trouble, and F, actual functional failure. This is the PF interval. To prevent a breakdown, our condition monitoring must happen inside this exact time frame. When proactive tasks are impossible, we move to default actions. If the failure carries an unacceptable safety consequence and we cannot predict it, we are forced to use design improvement, which means engineering the failure mode out of the system entirely. We also have run to failure. Strict engineering rules govern this choice. We only let a component run until it breaks if the consequence is purely economic and if the spare part is already sitting in the warehouse. Finally, we have failure finding tasks. We use these specifically for hidden failures, like backup emergency brakes or pressure valves. Because these devices sit idle, we schedule physical functional checks to ensure they will actually work when demanded. Letting a part run to failure or checking a dormant safety valve is not an absence of maintenance. They are calculated, deliberate engineering decisions backed by specific response plans. Before you commit to a condition monitoring program, you have to validate that the technology makes sense for the specific asset by running a 4-point checklist. Step 1. The degradation must be technically detectable. Step 2. The progression of the fault must be predictable. Step 3. The PF interval must be long enough to give your crew time to act. Step 4. The cost of monitoring must be lower than the cost of the repair. A common trap is the broken monitoring loop. If a sensor detects degradation but the warning sits in an inbox, the machine fails. Every digital alert must automatically trigger an actionable work order. This is an SAP PM interface displaying an equipment-level task list. Here we translate our carefully selected tactics into an executable, step-by-step plan. The task list has to define exactly what the crew will do, how they will do it, the specific trade skills required, and the safety lockout state the machine must be in before work begins. By directly attaching the bill of materials to these task operations, the system automates the logistics. The exact spare parts are reserved in the warehouse the moment the work order is generated. The most rigorously researched maintenance tactic delivers zero value on paper. It only becomes real once it is hard-coded into the ERP system as an automated execution plan. By following this methodology, you elevate your facility. You transition out of reactive firefighting and secure a documented, risk-prioritized, and system-integrated maintenance engine. However, maintenance tactics require ongoing review. You must track lagging indicators, paying close attention to your PM compliance rates and your mean time between failures. If an asset continues to fail despite executing the scheduled plan, that data serves as your trigger. You pull the failure mode back into review, analyze the gap, and adjust the tactic. You can start this transformation today. Identify your facility's top 5 critical assets, apply this framework to map their functions, and begin building your evidence-based strategy.